Hi, I'm Amir Hossein Mirza Bozorg, and in this video I wanna talk about Comprehensive Abacus Package Chapter 13, Writing Codes in Abacus Part 2. How to ask your video related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abacus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer a step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. This is the table of content for part 2 of chapter 13. Here I want to discuss about infinite elements. This is an example for writing keywords in Abacus and in IMP file. Infinite elements, they are used in boundary value problems defined in unbounded domains or problems in which the region of interest is small compared to the surrounding medium. Can have linear behavior only, provide a stiffness in a static solid continuum analysis, provide quiet boundaries to the finite element model in dynamic analysis. Standard finite elements should be used to model the region of interest, with infinite elements modeling the far-field region. Let me tell you about infinite elements. They are a special kind of elements in Abacus. Suppose a 2D example, a 2D problem. This is ground, and here we have a structure on top of it, okay? And we apply earthquake load here, okay? Earthquake load. We can apply acceleration or velocity or displacement. Then when you apply earthquake here, then mechanical waves will propagate in the ground, okay? They will propagate in the ground, and then they will shake the structure, okay? They will shake the structure. Also, for example, this wave will impact here, and then impacts here and here. So when the simulation is conducting, then if these waves cannot go out from the boundaries, then they will be reflected in the ground, and then it means that the earthquake is magnified, okay? But this is unrealistic. This is not correct. In the reality, they will go outside of the ground in also other regions, okay? And nothing is remained here. So we must define some boundaries here that allows the waves to go out, okay? So here we define quiet boundaries. They are infinite elements. Infinite elements. Infinite elements. Okay? When a waves go into infinite elements, then most of its energy is absorbed, and then a small portion of its energy will go back, will be reflected. Okay, we define infinite elements here, and we will use finite elements here. What I have taught you until now, all of them are included in finite elements. Okay, finite elements. Finite elements. But here we have infinite elements, because we don't want these waves to be reflected completely. Okay, they must be absorbed completely. These infinite elements can do this for us, so they are quiet boundaries, because when something impacts them, most of its energy is absorbed. Okay, they are quiet boundaries. And that's it. Plane stress, plane strain, three-dimensional and axisymmetric infinite elements are available. Reduced integration elements are also available in Abaqus standard. Here I want to tell you how to name infinite elements in Abaqus. We have generally we have two kinds of infinite elements. Some of them are acoustic infinite elements, and some of them are structural infinite elements. In this session, we will use infinite structural elements, not acoustic ones. If A is at the start of the name, it will be acoustic. This is optional. If A is not, then it is structural. And also, for example, for plane strain, it is PE. For plane stress, it is PS. And for two-dimensional 2D, three-dimensional 3D, axisymmetric AX. And also, this R is optional. For example, you can use reduced infinite element or full integration infinite element. In Abaqus explicit, I think we only have full integration ones. And also, these regions are named far fields. Okay, they are far fields. The solution in the far field is assumed to be linear, so that only linear behavior can be associated with infinite elements. In dynamic analysis, the material response in the infinite elements is also assumed to be isotropic. In Abaqus explicit, the material properties assigned to the infinite elements must match the material properties of the adjacent finite elements in the linear domain. It means that their Young's modulus and Poisson's ratio must be equal. Here, I'm gonna talk about infinite element mesh pattern. This is very important. This is very important. Before talking about this, let me show you several papers. In these two papers, they have used infinite elements. Here we have a bar for a non-destructive testing simulation, and here we apply excitation load, and then it is propagated in the bar to find this crack, this defect. Okay, and if you see, we have two black regions. They are infinite elements to absorb other waves. Okay, to absorb other waves. And also in this paper, this is the structure, this is its footing, and this is soil, and here we have infinite elements. Okay, infinite elements. Okay, except for explicit procedures, the basis of the formulation of the solid medium elements is that the far-field solution along each element edge that stretches to infinity is centered about an origin called the pole. This is pole. In this geometry, this is the pole. In this geometry, this is the pole. For example, the solution for a point load applied to the boundary of a Hopf space has its pole at the load's application point. It is vital that appropriately sorry it is vital to appropriately choose the node's position in the infinite direction with respect to the pole. Here, if you see, these lines are diverging from each other, or here they are parallel. Okay, we must use such patterns. We must not use such pattern. Okay, if you see, the lines of the infinite elements must be parallel or diverging. They must be parallel or diverging. They must not be like this. Okay, they must not converge. It's wrong. And the second node along each edge pointing in the infinite direction must be positioned to be twice as far from the pole as the node on the same edge at the boundary between the finite and the infinite elements. This point is not very important. Most of the time, even in the papers, they don't consider this point. In addition to this length consideration, you must specify the second nodes in the infinite direction such that the elements' edges in the infinite direction do not cross over. Do not cross over. Which would give non-unique mappings. Abaqus will stop with an error message if such problems occur. A convenient way of defining these second nodes in the infinite direction is to project the original nodes from a pole node. Minimizing the reflection of dilational and shear wave energy. During dynamic steps, the infinite elements introduce additional normal and shear transactions on the finite element boundary that are proportional to the normal and shear components of the velocity of the boundary. These boundary damping constants are chosen to minimize the reflection of dilational and shear wave energy back into the finite element mesh. This formulation only provides perfect energy transmission out of the mesh in the case of plane body waves impinging orthogonally on the boundary in an isotropic medium. However, it usually gives acceptable modeling to most practical cases. What does it mean? Please notice this formulation only provides perfect energy transmission out of the mesh in the case of plane body waves impinging orthogonally on the boundary in an isotropic medium. It means that in the 2D case, for example, we apply excitation load here, and here we have infinite elements. Then the induced waves will impinge on the boundary orthogonally. Okay? It is orthogonally, perpendicular. Okay? And if you do this, if the problem is like this, then the absorption is complete, 100%. But for example, if it is not orthogonal, for example, like this case, if you see, for example, this is not orthogonal, okay? So less than 100% will be absorbed and some energy will reflect. And that's it. During dynamic response analysis, the infinite elements hold the static stress on the boundary constant but do not provide any stiffness. Therefore, some rigid body motion of the region modeled will generally occur. This effect is usually small. It means that in this case, okay, if you don't, suppose that you only apply gravity load, okay? It means that when you apply gravity load, as we do not define boundary condition for the infinite elements, okay, then some rigid body mode deformations will happen. It means that it will move down, but there will be no problem. This movement is small and there is no problem here. For dynamic cases, the ability of the infinite elements to transmit energy out of the finite element mesh without trapping or reflecting, it is optimized by making the boundary between the finite and infinite elements as close as possible to being orthogonal to the direction from which the waves will impinge on this boundary. Close to a free surface where Rayleigh waves may be significant, or close to a material interface where Love waves may be considerable, the infinite elements are most effective if they are orthogonal to the surface. Rayleigh and Love's waves are surface waves that decay with distance from the surface. For example, if you see in this pattern, this is the best pattern for this geometry because in most of the regions the mechanical waves are perpendicular to the boundary of infinite elements. Okay, now I want to solve a problem using infinite elements. This is the problem. We have a 2D problem. This is a disk. As we have two symmetry planes, I only model 1/4 of it. And the inner radius is 0.2 and the outer radius is 2.2 meters. And here I will use infinite elements, and here I will use finite elements. And you can see the other characteristics of the problem. And here, according to this coordinate system, here we define x symmetry boundary condition, here we define y symmetry boundary condition, and we apply a pressure with this amplitude, and also I will mesh it and run it. Okay, let me open Abacus. Okay, I define a part named disk. It is 2D deformable shell, and I set the approximate size to 6, and I define the origin, I fix it, and I define construction lines. Very good. Do you have any question? You are very quiet.
Yeah, it's really new.
Yes,
it's learning now.
Yes, it's new for you and also the others, because yes, because it's you are right, it's very new. Okay, I want to partition it. In other problems, infinite element must have elastic properties, and other regions can have elastic, plastic, damage, and others. Also, in this case, I define two materials, but they are the same. Okay, they are the same, but I want to show you the procedure. Okay, only to show you the procedure. In this case, we don't define plasticity for this region. Okay, because it is not needed. But in other cases, maybe you need. So I should tell you the correct procedure. Okay, it is meshed. I go to the property. I define a material named finite element. Its density okay. It is defined. I create a copy from it and name it infinite element. Also, it only contains elastic. Okay, it only contains elastic. But in other cases, you must edit it and remove plasticity, damage, and others. So here I define a section named finite, solid homogeneous, finite, another section infinite. I assign finite here and infinite here. Okay, if you see, they have different sections and different materials, but they are the same, because in this case it was not important, but in other cases maybe it is important. I define a dynamic explicit step. Its time period is 0.001 second because it is very small, and I edit field output definition. I want to have 500 frames because I want to show you the traveling of waves, how the waves travel in the material. It's very interesting. In the interaction module, I don't do anything. In the load module, I define the pressure. If you see, 10 to the power of 6, 1 is 6, and I define this amplitude. It's a kind of impact. Okay, it's similar to impact. At 0, it is 1. At 5e minus 5, 5e minus 5, it is 1 again. In 5.1 e minus 5, it is 0, and also until 0.001, it is 0. Okay, very simple. And I define X symmetry for boundary condition. Here it is Xsim. Notice that we don't define boundary condition for infinite elements. We don't define boundary condition at all. Okay, this is a general rule for all of the problems which you use infinite elements. Okay, I go to the mesh. For here, I set it to explicit linear plane strain. Also for here, I set it to acoustic. If you use this, you will define acoustic elements, not infinite elements. But I define acoustic elements here because in the IMP file, then I search this element and I find the region which has acoustic elements, and then I change its element type to infinite element. Okay, then it is changed according to what I want. If I also set it to plane strain, then I cannot detect the region in the IMP file because all of them are the same. Okay, but when I change the element type in the CAE, also it is changed in the IMP file, and I can detect it simply. This is a trick. This is a trick. And in lines AB, AD, DE, EB, we want to have 40 elements. In BC and EF, 1 element. Along the infinite element, we must have only 1 element. So I select these regions 40, and in these regions only 1. Also, when you want to define infinite elements, that region must be meshed using the sweep technique. So I change it to sweep. Also, you must define the sweep path. The sweep path must be along the infinite elements, and it must going out. The direction must going out. Okay, outward. So this is correct. This is correct. Yes, please.
So even for the 3D model?
Yes. Even for the 3D models, it must be, you must use sweep technique, and also it must be outward. The direction, see the direction. If it was not outward, I should select another one. I should select another edge. But as it is correct, I click on accept highlighted. That's okay. And also for here, I use quad medial axis. Okay, I mesh it. No, it's not good. Why it is not good? Why it's like this? It is making me angry. Aha, very good. I want this. Okay, I have done everything. I go to the job, I create a job named job1, and I create its input file. Its input file is created. Now I open that IMP file. My Windows has problem. It's making me angry. What should I do right now? I edit it. I click on Control F and I search AC. These are the acoustic elements. But I don't want to have acoustic elements. I want to have infinite elements. So I must change it. What should I use if it is opened? I can tell you it is not working. I don't know why. So I must open it from here again. They have written Scene PE4, 4-node linear plane strain, one-way infinite quadrilateral. Scene PE4. So I change it. Scene PE4. Scene PE4. I save it. Now the element type is changed. Now I create another job named job2 from the input file. From the job1, I define job2. Okay? And I use parallelization. And I run the model. As this command was not in the CAE environment, I should add it from IMP file, and I did it, and now I define a job from previous job and I run it. It's very simple. Also, please notice that you must not import job 1 to the CAE environment again. Most of the students make this mistake. First, they edit the IMP file and they add their own keywords and then import it again. This is wrong because a CAE model is always translated to IMP file correctly. But an IMP file is not always translated to CAE model correctly. Also in this case, because the infinite element is not added in the CAE, okay? So it's wrong. Please don't do this mistake. And if you see it is running, it will be completed very soon. Yes, please ask your question.
During the running of the job, can you say it again about the importing the input file?
You must not import it. You must not. You must not import the IMP file. File, import, model. You must not, oh, here, sorry. You must not import the IMP file. This is wrong. Some people import the IMP file and then create a job from it. This is wrong. You must not import it. You must create a job and change the source to input file. Okay? It's important. And
Thank you.
You are welcome. And please look at here. It's very interesting. This is the infinite region. In Abacus explicit, the color of infinite region is gray always. But when you use dynamic implicit, its color will not be gray. Okay, it's the same as other regions. And here, until 5.1 e minus 5 second, until this time we are applying energy, we are giving energy to the model, but after it we don't do that. So please notice until this time we are giving energy to the model. Okay, until this time. And here you can see this energy, this wave, mechanical wave. Okay, okay. And let me tell you another thing. Please look at the value of von Mises stress. It's maximum. Please look at it and look at the contours. Please look at this value. And then it will decreases. It will decreases, see? It is changing dramatically. Why? Because the waves go and then during this travel, they are absorbed and then they go back. They go back with less than 10% of their energy, their initial energy. And then again they go here, they go back, and then their energy is absorbed because we don't apply energy again. We don't apply energy again. Please notice to this value, it is decreasing, it is decreasing, it is decreasing. Yeah. And if I continue the simulation, after some time it is near zero. Why? Because all of it is absorbed here. Because we don't define new energy. We don't apply new energy to the model. That's it. And if you have any questions, please ask. If you don't have, I want to go forward. Okay, I save it, and slides of IMP file are finished. So I go to the Python. I go to Python. Let me find my notes for Python. Where are they? They are here. Very good. Okay. Let me open no. Yes, that's it. Okay. I need these two files. Python scripting. Very good. In Python language, capital or small is important. For example, in Fortran, it is not important. If you write with capital letters or small letters, it is not important. But in Python, it is important. And here, I'm calling the libraries from Abacus import, from Abacus Constance import. I'm calling libraries, and then I'm defining values, some values, and also other commands. I have written them here. I have written a comment for them. And let me run it. No, sorry. I run this script. The CAE model will be created automatically, then the job is created automatically, and finally the simulation will be done. What? We have a problem here. Aha. Where are the parts? It is so. Aha. The model is test 1. The model is test 1. Here, if I must change this directory. I must change this directory. I think I must use this directory. Control C and Control V, Control Z. Aha. Why slashes are? I think I must change the slash directions. Why they are form? Okay. Uh, uh, the script is running. For example, here if you see 976 elements have been generated. Yeah, it is done. If I show you the model is this beam with one hole, and we have the property. We have it is even partitioned. This is a step definition, no interaction, load definition, and here we have the mesh. All of them are defined automatically, and here we have the result. Yes, that's it. So I save it and I close it, and I create another folder. I put it here. And here, if you see, we have a for loop here. And in the Python, the index of loops starts from 0. Okay, it starts from 0, and loops don't have end command. They are distinguished using indents. Indents make distinguish between loops. And also I must change this directory. Very good. Very good. Now I open Abacus again, and you will see that several models will be created and they will be run automatically. It is very interesting. Python scripting in Abacus is very interesting, but I myself, I'm not expert in Python scripting in Abacus. I am expert at writing subroutines, and even I will give its course in the future. It's for subroutines, for writing subroutines. I'm not very good at writing scripts. I think 4 or 5 models will be created. Test 1 is created. Then test 2 will be created. Then test 3 will be created. Then test 4 and I think also 5 and 6. I don't know. Job beam 2. The other one is running. Also the other one. One after another. One after another they are running. For example, suppose that you must create and run 100 models and only 2 or 3 factors are different in the models. So you can write its script and then run it and then go out. For example, go on a trip. And then when you go back, all of the models are created, all of the simulations are done. It's very interesting. This is the power of Python scripting. It is completed. If you see 5 models are created, model 1, model 2, model 3, model 4, model 5. The position of the whole is changing. Okay? It's very interesting. And all of the other settings are the same. Do you have any question? If you have any question, please ask. If you don't have, I want to go to the next chapter. I don't want to explain more about Python scripting because this class is not for Python scripting, okay? But I will give you all of these codes, okay? They have comments. You can read it yourself. You can read it yourself. But understanding it for the first time is very hard, okay? It's very hard. I know. That's it. So here, now I want to go to the next chapter. It is related to heat transfer analysis, and also in that chapter I will write a subroutine. I will write dflux subroutine from the beginning, and you will learn how to write subroutine, some simpler ones. Okay, this is the end of chapter 13. Thank you so much. How to purchase packages or individual chapters. Each of the packages and individual chapters includes CAE journal and IMP files, step-by-step tutorials with detailed explanations and investigation of the results, slides and reference papers and standards. Packages specifications and payment details are provided in the video description. Also, you can pay the cost of the packages in 2, 3, or 4 installments according to your budget or income. In the future, updates will be provided for free for everybody who purchases each chapter or each package. The cost of each chapter or package will increase after each update for new buyers, but those who purchase the package would have endless access to all the upcoming updates. This will make the content up to date for new needs and new problems which must be solved via FE simulation. You can contact us using Telegram or WhatsApp, or you can send email to us. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects. We offer support in writing the modeling and result discussion part of your thesis. And we have consulting services for MSc, PhD positions or job interviews, and we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.